Good afternoon, everyone. I'm Nutan Nepal. I'm from North Carolina State University, and my advisor is Jacob Mathon, who gave a talk on Lorentzian polynomial this morning. Today, I'm going to be talking about induced Lorentzian polynomial. This is based on joint work with Chris Yor from Carnegie Mellon University and Daniel Chen from UC Davis. Daniel is here in the audience with us, and he has volunteered to take on top questions. So, if you have any next door to ask him. Anyway. So here is the archive number. So Jacob already defined what Lorentzian polynomials were this morning. So I'll be moving through my first few slides pretty quickly. So Lorentzian polynomials were introduced by Ramjian and He in 2020. They serve as the multivariate analogs of log-concave polynomials. And here's the definition. We call a homogeneous polynomial with non-negative coefficients Lorentzian if it satisfies the following two conditions. The first one is that its support must be M-convex, if you remember from this morning. The second condition is that if our polynomial has more than degree 2, then we can just start taking derivatives in different orders, and the quadratic form associated to the resulting degree 2 polynomial must have at most one positive eigenvalue. Here are some pictorial examples of M-convex sets. If we want more examples, we can always take the lattice points of S polytope of any polymatrix, and they would work. Here is an example of Lorentzian polynomial. I think Jacob did the same example this morning, so I'm sorry. It's pretty small. This is Lorentzian because the support is M-convex, and then the quadratic form associated to it is this. It has the eigenvalues 2 and 0, at most one positive eigenvalues, so it checks out. The second polynomial here is not Lorentzian. How do we see that? Okay, so we can see that by just checking its support. Turns out that this polynomial does not have the center point in its support, which is it. All right. So with the definitions and examples done, I would like to present this problem to you. So if we have a party of n people whose expertise collectively cover key topics, and suppose we also know that which people are experts in which topic, right? And what we want to do is for any given subset T of topics, we want to form a panel of the same size as T, such that T can be covered by assigning a distinct topic to each panel member with the expertise, right? Now, with this, for each given T, what we can do is we can count the number of such panels that we can form. And we call that number the matching statistic. One thing to note here is that for subset T, there could be multiple ways that we can form the same panel. However, we are not counting the number of ways, we are counting the number of panels that we can form, right? So multiplicity free thing. Okay. Now, let's say we fix a natural number R less than n, and we try to vary all the subsets T that have that size, right? And let's say we record these numbers, these matching statistics for the subset. Then turns out that these numbers exhibit a very nice property. I'll show it to you. So let's fix these notations. Turns out that if we write those matching statistics in this certain way, then these polynomials happens to be Lorentzian. Okay. Now, to show some polynomial is Lorentzian, what we usually do is we start with the polynomial that we already know is Lorentzian, and then we apply a bunch of Lorentzian presuming operators to get the desired polynomial. But however, for this polynomial, what we needed to do was we needed to define a new operator which preserves Lorentzian, right? So for the remaining of the talk, I would like to show you that operator and how we can get this polynomial from that operator. Okay. So let's say we have a set system. What we can do with that is we can make a bipartite graph out of it. I'll show it to you with an example. say the set system is 1, 2, 1, 2, 3. You can quickly get this bipartite graph. It just means 1 and 2, they are export in the topic 1, and 1, 2, and 3 are all exports in the topic 2, right? Now, with the bipartite graph, we have a concept of matching. We say that alpha is g to the k, which is the number of vertices on the left, matches with beta in g to the k, which is the number of vertices in right. If there exists some subgraph that has alpha as its left degree vector and beta as its right degree vector. Again, we can see that with examples. So the vector 1, 1, 0 matches with 2, 0 because of the existence of this subgraph I left it in red. Similarly, 1, 1, 0 matches with 1, 1. Actually, 1, 1, 0 matches with 1, 1 in 2 different ways, but we don't really care about the number of different ways, as I said. Right? And finally, 1, 1, 0 matches with 0, 2. Okay. Now, time to define the operator. So this operator that I mentioned before, what it does, it maps the scale monomial x to the alpha over alpha factorial to the sum of y to the beta over beta factorial for all beta that matches with alpha. Okay. And then we extend linearly to all polynomials. Using previous examples, since 1, 1, 0 matches with 2, 0, 1, 1, and 0, 2, we say that the monomial x1, x2 matches to this polynomial number. Okay. Now, since this was a fairly small example, I decided to compute the images of all the monomials that give rise to non-zero, that map to non-zero value, right? And one thing we can quickly check from the definition is that all monomials that have multi-degree greater than 2 to 1 for this, they are automatically mapped to 0. Okay, so with the definition of the operator, we have the following result, as alluded before. For any set system S, this operator, which we are calling the inducing operator, it preserves Lorentzian polynomial. Actually, the operator is a little stronger. It also preserves volume polynomial, but due to time constraint, I'm talking about it. And as a corollary, what we get is this polynomial that recorded the matching statistic I showed before. Turns out that polynomial is Lorentzian, and we can see that this polynomial is actually the result of taking the multi-affine part of the image of the elementary symmetric polynomial under this operator. Yeah. And taking multi-affine part also preserves Lorentzian. So that's it. Thank you.
Do you have a question for Nutan?
Yes. Does the operator JS preserve normalized Lorentzian or just Lorentzian?
So okay, denormalized Lorentzian.
Say.
Yeah, I think we checked this too, but I don't remember either. Sorry. Any other questions? I think I'm done.
That's where they're using the symbols.
Oh, yeah. So we proved this using the symbol theorem. We saw that the symbol of this operator actually is the exponential generating function of some polymetry. Okay, of the lattice points of this polymetry.
All right. Looks like usually I got that.